Now let's talk about combinatorics. Combinatorics is all about how to count the number of elements in a given set very effectively. So being a computer science engineer, why do we require it? Ask yourself. So there are a lot of problems in computer science requires these basic counting skills. I'll show you some of the problems. There are so many, but I'll show you a few. One is IP address problem. So any computer which is connected to internet requires IP address. Then the number of computers which are to be connected to internet decided by the number of IP addresses we can generate. But generally we use 32 bits for IP address, otherwise some bits for IP address. Then using that bits, how many IP addresses we can generate is the question you have to answer, because that decides number of people to be connected to internet at a time. Correct? That's why it's very popular problem. You require combinatoric skills to solve it. Second one, let's say Google company has Gmail, right? So Gmail gives you IDs, like every customer who uses Gmail requires an ID. Then the question is how many IDs you can generate decides the number of customers Gmail can have. Suppose let's say Gmail, for simplicity it may not be true, Gmail is using only three positions, like it is allowing only three position mail IDs. That means three length mail IDs. So every mail ID should have three letters. Then only English characters are allowed, like A, B, C, so on up to Z. If that is a question, then how many IDs we can generate? If you know that, then you will decide how many customers Gmail can have, isn't it? That's why that's interesting problem for them. Take the third problem. How many variables a program can generate? Let's say your program again is restricted to use only two positions or three positions, let's say, for generating the variable. So that means each variable should have three positions exactly, and only English alphabet is, let's say, allowed. Then probably how many variables you can generate for a program, that decides the program's capability, isn't it? Example, you want more variables than what actually can be generated, then you will be in trouble. You can't write a program, right? So that's why here one interesting question is how many variables actually we can generate in a program, decided by the structure of the variable, right? So this problem also requires again counting skills. Fortunately, there are so many problems, like lot of problems can be solved with simple strategies. That's why we have to learn these combinatorics. Let's begin with two such simple rules and very important rules. One is sum rule, second one is product rule. Let's begin with sum rule. Sum rule is like this. I have a set S. I don't know how to count it, but I know how to count a set called S1. I know how to count a set S2. So how it is related to your problem S? Your problem S is nothing but union of S1 comma S2. That means counting a set S is nothing but counting S1 union S2. If that is the case, then the total number of elements in set S equal to total number of elements in S1 plus total number of elements in S2. This is called sum rule. But the only condition here is S1 intersection S2 equal to empty. That means there is no common element between S1 comma S2. Then only we can apply this sum rule. You should be very careful before using it. So please always ensure that there is no common element between S1 comma S2. Then go for this rule. Example, let's say Raju is a small kid, okay, a 4 years old, and he has some chocolates, okay. So that is set of chocolates, something around 30, let's take, and he has some biscuits also with him. Let's say SB denotes set of biscuits. Assume that the value of SB is, let's say, 50, and here I am assuming set of chocolates equal to 30, and he knows that chocolates and biscuits are different objects, and he want to count the total number of food items he has. So the total number of food items he has equal to SF, which can be denoted as set of chocolates union set of biscuits. Now this is exactly a sum rule problem, right? So here the total number of food items according to the sum rule equal to total number of chocolates plus total number of biscuits. Since we know that chocolates and biscuits are mutually exclusive, we can apply sum rule. So answer will become, so total number of chocolates 30 plus total number of biscuits 50, hence it is 80. So this is a way we can use sum rule. Let's talk about product rule. Product rule is like this. You have a task T, okay, and you don't know how to do it also. But what is unknown is the total number of ways of doing it. Example, take an example of Raju. Raju has 5 shirts, let's say, and he has, let's say, 5 jeans. Now the question here is how many different ways he can wear a dress. But Raju knows how to wear one dress. For that he wear a shirt followed by jeans, isn't it? But what is not known for him is finding the total number of ways of wearing a dress. So that is a task. So how many different ways he can wear dress is a problem for him, and how he can solve it. For that we apply product rule. So according to product rule, whenever you have a task T and you don't know how to do it, then you please divide into some sub problems such a way that you know how to solve them. Okay, then happily we can apply product rule. So according to product rule, whenever you have such problems, then total number of ways of doing this big problem equal to total number of ways of doing T1 into total number of ways of doing T2, so on total number of ways of doing Tn. This is the product rule. But here one essential condition is T1 and T2 so on Tn are mutually independent. So I will tell you what is the meaning of independence with one example. Let's take same example of Raju. Raju want to wear a dress. For that we can do the task by two subtasks. One is wearing a shirt followed by wearing a jeans. Isn't it? Whenever Raju wear a shirt followed by wear a jeans, always he ends with one dress. Correct or not? So that's why this is called a task sequence for wearing a dress. Whenever you have this kind of task sequence, then we can apply product rule. So before that I have to prove that these two tasks are independent, correct or not? So what is independence here? I will tell you with this example. So let's say Raju has 3 shirts. Let me take like this. Raju has 3 shirts and Raju has, let's say, 5 jeans. Okay. Now wearing a dress is nothing but choosing a shirt. Let's say shirt number 1 followed by choosing a jeans. Let's say jeans number 1. Right? But for same shirt number 1, he also can wear either jeans number 2 or jeans number 3 or jeans number 4 or jeans number 5. Isn't it? But if he changes the way of wearing shirt to S2, that means he changed the shirt to S2, then again, so Raju has same 5 number of ways of wearing a jeans. Isn't it? So that is called independence. Irrespective of the way of doing the task number 1, still if you can do the second task in same number of ways, we say that that kind of tasks are independent. Whenever tasks are independent, always we can go with product rule. We can apply the product rule to calculate the total number of ways of doing the original task. So we'll apply that now. Example, total number of ways of wearing dress, if you want to know, according to the product rule, it will be total number of ways of wearing shirt into total number of ways of wearing jeans. Since wearing shirt and wearing jeans here are independent, then total number of ways of wearing shirt here, example 3, right? 3 into total number of ways of wearing jeans here, since he has 5 jeans, 5. So 3 into 5, 15. Correct? So in that way, we can find out the total number of dresses possible. Let's discuss some problems related to product rule. First, start with this problem. The number of binary sequences of length n. Let me take n value 3 and understand the problem. Let's take 3 positions. the number of binary sequences with 3 positions. For that I take 3 different positions. So any binary sequence can be formed by writing 0 or 1 or 0 or 1 or 0 or 1, isn't it? So now once you do it, then you realize that forming a binary sequence is nothing but it can be done by task sequence. So that task sequence is, because to form a binary sequence you are filling the first position and you are filling something in the second position and you are filling something in the third position. In that way you can divide your problem into 3 subtasks. Okay, so forming a binary sequence exactly equal to filling the first position followed by second and third. So now I designed the task sequence. When you have task sequence and you know the total number of ways of doing each such subtask, isn't it? So total number of ways of doing the problem number T1. What is this T1? Filling 0 or 1, isn't it? So that's why you can do it in 2 ways. Similarly, filling the second position can be done in 2 ways. Similarly, filling the third position. And tasks are also independent. Why? Because whatever the way you fill the first position, still you have 2 independent choices to fill the second position. And whatever you fill in the third position, still you have 2 independent options to fill the third position. That's the reason I say they are all independent. Whenever tasks are independent and when you have a task sequence, so you apply directly product rule. According to the product rule, total number of ways of doing the original task T equal to the total number of ways of doing subtask number 1 into total number of ways of doing the second task followed by total number of ways of doing T3. So now multiply them because product rule says that, right? So using the product rule we can multiply them, then it will become 2 to the power of 3. For general value of n, it is for n value 3. What if I take exactly n positions, then your task sequence will become T1 followed by T2 followed by T3 so on Tn, isn't it? So you will have n subtasks, each can be done in 2 ways and all are independent. That's why the total number of binary sequences will become 2 to the power of n rather than 3 if I take general value rather than a particular 3. Correct? Let's go to the second problem then. The numbers between 0 to 9999 which contains exactly 15. So first of all, any number between 0 to 9999 can be visualized with 4 positions. Okay, so visualization is very important in combinatorics. First understand the problem and represent it. So now my problem is nothing but forming a number between 0 to 9999. Then I have this representation. So it is easy to represent. Then example, let's say my number is 23. So how I represent 23 here is I write 0, 0, 2, 3. Correct? So now similarly, if you want to represent 1, then I can write 0, 0, 0, 1. So finally what I want to say is any number between 0 to 9999 can be represented with 4 these positions once it is over. But our problem is not only representing any number, but that should contain exactly 15. So for that what I do is I take 4 positions and I think about forming one such number which is our solution. So any solution definitely contains exactly 15. Then to do that, like to form such number, so I can simulate this is procedure. What is that? I write 5 first somewhere, followed by I fill the remaining 3 positions without 5. Whenever I do that, I always end with what? A number which contains exactly 15. So now if you see my process, then you understand the task sequence. Okay, so that's why always I do this procedure. Whenever you want to design a task sequence, first of all understand the problem. Based on the problem, try to form one such solution. When you are forming the solution, you realize the way of forming the solution, then that will work like a task sequence. Now here my task sequence is, first task is I fill 5. Then second task is I fill the remaining 3 positions, but I remember that I should not fill 5. Whenever I do these 2 tasks one by one, let's say T5 followed by T triple dash, always I get a number between 0 to 9999 which contains exactly 15, isn't it? So that's why this is my task sequence. One of the important property of task sequence is should prove that you should understand that otherwise that your task sequence T generates all possible solutions. Example, I prove that my task sequence can generate any solution. Example, one of the solution is 2, 3, 4, 5. So this 2, 3, 4, 5 can be generated by my task sequence. Since my task sequence says that T5 first, that means T5 is what? Filling 5 somewhere, then I can fill 5 here. Okay. So because my target is forming such number 2, 3, 4, 5 with my given task sequence. Yes. Now this task is done and I filled 5. Now I have to form 234 by filling these 3 positions. Since my task is filling 3 positions without 5, then by doing that still I can ensure filling 2, 3, 4 here. Isn't it? So that's why what I want to say finally, so 2, 3, 4, 5 can be filled with this task sequence. Similarly, any number between 0 to 9999 which contains exactly 1, 5 can be then definitely represented by this task sequence. Once you have a proper task sequence, then you apply the product rule. So why we can apply product rule here is because these two tasks are also independent. I prove it now. Whatever the way you fill 5 T5, example, what is T5 here? Filling 5 something somewhere, right? Example, if you fill 5 here, then these 3 positions can be filled in, these 3 positions can be filled with some ways, I don't know, whatever. But if I change the position of 5 here, still these 3 other positions can be filled with same number of ways. Okay, so that's why these two tasks are independent. So first we see the total number of ways of doing T5. Since you know that the task T5 is nothing but filling 5 somewhere in 4 positions, then you will have 4 options, isn't it? Now T triple dash. So T triple dash is like this without 5, correct? So T triple dash is, once you fill 5, then in other 3 positions we have to fill the other 3 positions should be filled, correct? So already 5 is filled, then you have 3 positions. We cannot use 5 again, then the problem will be like this. Now there are 3 positions, sum 3, and in every position we have to fill other than 5. Then you can fill 0 or 1 or 2, 3, so on 9, but other than 5. Then there will be 9 options for it, isn't it? Now similarly for second position also, other than 5 you will have 9 options. Third position also, other than 5, 9 options. When you have 3 positions and each position can be filled in 9 ways, according to the example number 1, this formula will become 9 to the power of 3. The total number of ways will become 9 cube, isn't it? So every task here, I can imagine like 3 subtasks. Every task can be done in 9 ways. Then 9 into 9 into 9, 9 cube ways you can do the second task. Now come to the original problem. You have a task T, that is nothing but T5 followed by T triple dash. T5 can be done in 4 ways. T triple dash can be done in 9 cube ways, and they are independent. Wherever you fill 5, then you can fill the other 3 positions with 9 cube ways, isn't it? So that's why the total number of ways of doing our task T equal to total number of ways of filling 5 into total number of ways of filling the 3 other positions without 5, of course. Then that will become 4 into 9 cube. In that way you can answer this question. And it is related to product rule. When couples are invited to a party with the condition that every husband should be accompanied by his wife, however a wife need not be accompanied by her husband, the number of different gatherings possible at the party. So if you see this question, I can easily understand this by taking a couple. Let's take one couple called Raju, Rani, and the conditions are every husband should be accompanied by his wife. That means whenever Raju wants to go to a party, then Rani should accompany him. Second one, however, wife need not to be. Rani alone can go without Raju. Third one, if someone invites you to a party, then it is not compulsory that you should go, right? If you have some other work, why should I go? That's why this is the reason we form empty gathering. So there are three possibilities we can have in a gathering if some couple is invited to a party. So similarly, if I take one more couple, let's take Rakesh, Vani. Since every couple has same terms and conditions, they also form three gatherings. One is Rakesh, Vani. Second one only Vani. Third one nothing. So in that way, every couple's decision can be represented with three numbers. One is 2, second one 1, third one is 0. Isn't it? So similarly here also 2, 1, 0. So finally, these two couples' decisions are deciding the gathering. Yes or not? Example, if I write 0 and 0 here, then this is about empty gathering. That means no one is in the gathering. Now, if I take 2, 2, that indicates that so Raju, Rani, Rakesh, Vani, everyone present in the gathering. Now, by changing this 2 to 2, let's say 1, 0, that means 1 means Rani, 0 means nothing. That means only Rani is in the party. In that way, this ternary pattern with two positions decides the gathering, isn't it? So now problem is reduced to how many different ways you can fill these two positions, where every position can be filled with 0 or 1 or 2 or 3 ways. Then answer will become 3 square according to the product rule. But the question is not about two couples, isn't it? So this is about n couples. When n couples are invited, then I can extend this problem to n positions. Let's take n positions, and each position represents a particular couple, and there are n couples, so n positions, and each position can be filled by 0 or 1 or 2, and the possibilities already discussed. Then each position can be filled in three ways, and there are n such positions, then the total number of gatherings possible equal to 3 to the power of n. So answer is B. In that way we can easily answer questions related to product rule. Numbers between 0 to 9999 which contains exactly 1, 5 and 1, 6. We know that any number between 0 to 9999 can be represented by 4 positions, isn't it? Now, but it should contain exactly 1, 5 and 1, 6. So what I do is, I always think about forming such sequence like one number which is exactly a solution for my problem. Then I get like this, maybe 5 here, 6 here, something 2 here, 7 here. So this is a solution for our problem, but we want to count the total number of such solutions. Then writing 5 here, writing 6 here, something 3 here, 9 also will give you some solution. Then while observing the solutions, I realized that I should write some 5 somewhere, followed by I should write 6 somewhere in the remaining positions, of course, and I have to fill the remaining 2 positions. Whenever I do that, I end with one possible solution. Any possible solution can be done by this process. But only thing is that two positions cannot be, in that two positions we cannot fill 5 and 6. So no 5, no 6. Then I got the task sequence. And the only thing is, we have to prove that these three tasks are independent, and we have to find out the total number of ways of doing them. Example, how many ways I can do T5? What is task 5? Filling 5 somewhere when you have 4 empty positions. When we have 4 empty positions, I can fill 5 in 4 ways, isn't it? Example of that is like this. Second one, filling 6 somewhere after doing T5. After doing T5, already 5 is filled, then you will have 3 different positions. We have to fill 6. Then we have 3 options, isn't it? Now I want to say that wherever you fill 5, filling 6 always will be done in 3 ways. Example, if you choose 5 here, that means if you fill 5 here, still you have 3 other options for 6. If I choose 5 here, then 3 other options we have. So I want to say that that's why the number of ways of filling 6 is independent of number of ways of filling 5. T5 and T6 are independent. Similarly, I can prove that T double dash also independent. Wherever you fill 6 after filling 5, these two other positions can be filled in same number of ways. That's number of ways are, let's say T double dash equal to filling these two positions. Since each position can be filled by only 8 ways, then according to product rule, this will be 8 into 8, 8 square. So that 8 ways are 0 to 9, other than 5, other than 6. Generally we have 10 ways 0 to 9, but out of them 5 and 6 cannot be taken. Then the total number of ways are 8 and 8. Hence it is 8 square. So now come back to the original problem. How many different ways you can form such sequences? Equal to T5 followed by T6 followed by T double dash. Then according to the product rule, the total number of ways of doing such task equal to total number of ways of doing T5 into total number of ways of doing T6 followed by total number of ways of doing T double dash. So T5 equal to 4 and T6 can be done in 3 ways and T double dash can be done in 8 square. Then it will be 4 into 3 into 8 square. So this is the answer for the problem number 1. Let's go to the second problem. The number of palindromes of length 7 using English alphabet. So any palindrome, of course, will have this property. That property I'll show now. First of all, there are 7 positions. 1, 2, 3, 4, 5, 6, 7. Any palindrome will have this property. The value at position number 1 will be equal to value at position number 7. Similarly, value at position number 2 should be equal to value at position 6. So position 3 should be equal to position 5 and 4 should be independent. Isn't it so? So now, if that is the reason, now easily I can find out the total number of palindromes by this method. What I do is, I realize that finally I have to fill every position. I can't escape that. So by filling this position carefully, I can form any palindrome. So let's design a task sequence. T1 followed by T2 followed by T3 followed by T4 followed by T5 followed by T6 followed by T7. Because every position should be filled, but appropriately, and we should remember the conditions about palindrome. That is, 1 should be equal to 7, 2 should be equal to 6, so on. Let's do that quickly. How many different ways you can do T1? Since this is the first task, we have not at all filled anything. Then when you have 7 empty positions, and now we are filling the first position, this position can be filled with 26 ways because we are using English alphabet. There are 26 letters in the alphabet, so 26 ways we can fill. Now T2, the total number of ways of doing T2, filling the second position. Since 1 and 2 are independent, up to now only 1 is filled, 2 can be filled in 26 independent ways, isn't it? Now similarly, T3 also can be done in 26 ways because it is not depending on T1 or T2, like that 26 ways are independent of T1 and T2. Now T4, which is nothing but filling the fourth position, that is not at all depending on anything, then still you will have 26 independent options. Now when you come to T5, so T5 is nothing but copying the value from the third position. Already the T3 task is done. Whenever T3 task is done, you are filling some value here, example A, then same thing you should write in the fifth position. That can be done in exactly one way. That's why mod T5 equal to 1. In the same way, mod T6 also 1, mod T7 equal to 1. According to the product rule, the total number of ways of forming palindromes is nothing but filling all 7 positions with these possible ways. Then it will become 26 into 26 into 26 into 26 into 1 into 1 into 1. That is nothing but 26 power 4. So there are 26 power 4 palindromes with 7 positions where alphabet is English alphabet.